Let's try to solve an interesting problem. Don't know if I'll solve it or not, but it seemed interesting. So the problem description is: there's a strange printer with the following two special requirements. On each turn, the printer will print a solid rectangular pattern of a single color on the grid. This will cover up the existing colors in the rectangle. Once the printer has used a color for the above operation, the same color cannot be used again. You are given an M by N matrix target grid, where target grid row col is the color of the position row col of the grid. Return true if it is possible to print the matrix target grid, otherwise return false. And then there are some examples. So we can see color 0 is printed, then we print color 1, and then in a rectangle color 2, which is valid because we've used every color only once and we've only printed rectangles. And here's a slightly more complex example where we start again with one color, we print it all over with a single solid color, then in the corner here cut out a bit, cut out a bit. Would have been nice for them to provide a visualization of why this is impossible, but this is a checkerboard pattern, and there is no way for that to happen. If we think about it, let me just pull up like GIMP or something. It'll take a second, I'm sorry. And I need to capture it as well. Add sources, capture, add source, add new source, GIMP, add source, and yeah, okay. Let's create just new canvas, doesn't matter. And essentially, if we fill this with a solid color, the pattern we have is a checkerboard. So it's going to be a different color here, different color here, a different color here, a different color here. Now, there's no way of producing this, because for the black color to be, let me pick a brush. Is this a brush? And a different color? I'm sorry, I'll set this up eventually. All right, I'm still in selection mode. Anyway, brush. There we go. In order for us to print these here in the corners, we must have printed the entire thing black. But in order for us to print these here, for example, we must have printed at least a rectangle of this shape. So this one would be white as well. And we can't really use black. So a checkerboard pattern is not possible. Let's close that. And we have some constraints. Constraint is that this is actually rectangular. Our dimensions is at most 60 wide and high. And we have at most 60 colors. It's good to know in case we have to do some optimization. I'll be working in Kotlin. The specific language shouldn't matter. I hope this is zoomed in far enough. But how would we approach solving this? What do we know? We know we can print print a rectangle of a color we can use a color only once. We can only use rectangles. And the question is it valid? Is this printable? So thinking about the structure of the problem, the immediate approach that I'd think of is to just try to reconstruct which rectangles were used or reasonably used, and then check if with those rectangles we can create a valid result. So let's say create a draft, detect used rectangles somehow, detect if those rectangles were used in a valid fashion. I have no worry about this part. This should be fairly straightforward once we have these rectangles. Essentially, we have a hierarchy, as a tree hierarchy of how we drew, right? So we could just reconstruct the order of operations as a tree. And if we find such a tree, then it's printable. If there is no such a tree, and we need to build some sort of cycle or if we have to use some sort of cycle in the hierarchy, then it's not a valid pattern. So I'm imagining we'll do checks like rectangle of color X contains or intersects. No. Contains would mean another rectangle covers part. Oh, let's call it covered by. Covered by rectangle of color Y. This here is not allowed to be a cycle. No cycle for this. That means valid. If we find a cycle, it's invalid. How do we find the rectangles though? We can deduce the minimum size of rectangle used by finding the corner. No, the corners don't help us. The extreme points. So if we look at this, we know the original one had to cover, well, if we look at this example, we know the original one had to cover the entire field because the top left corner, if we start, well, the box has to start top left, and we know it spans to at least the last row and the last column because there's an entry in the last row and last column. We know the 3 corner here, and there's nothing to the left of it, so we know that the minimum sized rectangle starts at coordinate 2 and 1 on the y-axis, and extends at a maximum to 3 and 4. And the same for the other. So we can use that to detect each rectangle. We can just go through the extremes, basically. Right? Yeah. x1 top left x, top left y, top bottom right x, bottom right y. So we can use this object to model our rectangles. Next, we want to detect them somehow. So let's create a list of rectangles. And we can do the brute force method of, for every color, we're gonna use a process for rectangle. We could also use a map to find the relevant rectangles. Sure, let's do that. So I'm thinking we have some sort of map containing map color to rectangle, and we want to then update, iterate over the grid, and update the corner, the respective xy based on discovered color. So then the rectangles shouldn't be a list anymore. This would be a mutable map of integer, our color, to our rectangle. And now we want to iterate through the entire list. So for target grid for each row, and row now we want the indices I believe that was the function. I don't like the leetcode editor without autocomplete. Anyway, we can just use plain for loops. Let's use them for I have not used a plain for loop in so long. Just a second. I just realized that would still require that we get our x and y coordinates out of, so it might as well just do it this way then. So you can imagine this like if you're coming from JavaScript, that this is the same as the JavaScript for each, except we're using different brackets here. That's the only difference. And indices converts it to the list of indices instead of the items. So in JavaScript, you'd write index here. So that's all it is. And this is the column. And the color in question. And if it irritates you that I sometimes write color with O and sometimes with OU, I'm sorry. So for the color is the target grid. Row call. And now our current rectangle is equal to the rectangles of the color, or that is the nullable coercible in Kotlin, or it's a new rectangle if there was no rectangle and its position would be for x would be the column, row, column, row. So it has size 1 at this point. It's just covering that one spot that we discovered. So let's say we just went through we started iterating, we found the 1. We just create the rectangle at this exact point. And as we discover more of 1, we'd expand the rectangle as we scan across. And once we discover the 3, we'd create a single cell 3, and then we'd expand it across as well. Oh, I can completely collapse it. Great. Okay, so we've got the rectangle, row, and I might switch to a proper code editor in a second. Now we can create a new rectangle. That is the expanded rectangle. And that is the old rectangle. And we copy it. And we override all values. So we could just create a new rectangle as well, actually. And the x1 will be the... I can never remember whether leetcode has min-max or not. I think it doesn't actually have min-max. So let's just quickly add it. And that is equal to x smaller y, then x otherwise y, and max looks the same, except we're flipping those. Right, so we can use min-max now. So the top left, we want to recede. So if the new column is smaller than the old column, we want to take the new column as the new min. There's no example here for it, but let's say the 3 was cut off here as well, and we discover this one first. Then when we discover this one, we want to expand the rectangle outwards towards to this point. So that's what we're going to do here. So we have the column, the same thing for the row, and this is y1. And we'll do the same thing for the other side, except it's a max and over the other corner. And then we'll write it back to our map. Rectangles, color as our expanded rectangle. I don't know why I keep doing those. Those are not necessary in Kotlin. Okay, so this fetches us all of our rectangles. So at this point, construct all our rectangles. Once we have them, now we need to detect, do we have a cycle? Cycle detection. What do we need for the cycle detection? We need to figure out if a rectangle is part of another rectangle. So let's extend our rectangle class. Well, in this case, it's an extension function, doesn't matter. If it includes a specific XY point. Or, yeah, let's do that. Which is a, my God, I don't remember, really. Is it Boolean or bool? Boolean, okay. When does a rectangle include a point? Well, when any of its coordinates are basically larger. So we can return x1 is to the left of x, and x2 is to the right of x, and y is below y. Oh, I flipped them, yeah. And y1 is below y, and y2 is above y. Right? So x1 is to be smaller, larger, smaller, larger. Yeah, so this should successfully check if a point is within a rectangle. And now we need to determine somehow which rectangle contains what other rectangles. And we could do that by checking if they include any of their color. So figure out which rectangle contains other rectangles. Let's make it a map again, and this time the map is going to be color to list of color or set of color. And we can read this as the rectangle belonging to this color contains or is covered by the rectangles of these rectangles. Is covered by, say, mutable map of int to set mutable set of int. Did I write it up here correctly? Of. And we want to iterate through our array again. Pretty much exactly the same way we did here. So let's just copy this part. Can actually copy this part as well. Okay, so we have our color at that spot. And now we want to go through all of the rectangles we found. Sorry, let me drink something. Right, now, now we iterate over our arrays, our rectangles. So we can go through each rectangle, and this is the key, so we can call this rectangle color, and this is the actual rectangle. And if it's an error, if the rectangle, if the rectangle is the same color, we ignore it. So if rectangle color equals color, it's not the same color and the rectangle contains includes row column, then I have inconsistent tabs here. I'm missing a closing one apparently. No, I'm not. Why am I? There we go. Is it also up here? No. Okay, whatever. Okay, so if the rectangle is not the same color and it includes the current color as in the current coordinate, then we want to add it to is covered by. So covered is covered by color rectangle color, and if that's empty, then it should be a a new set, and we're going to add the color we discovered to the set, and then we're going to write it back. So in theory, we should get the things, the rectangles we covered, and now we just need to do cycle detection. But before we do that, let's just return false by default. And let's print the rectangles we get out here. And let's print the is covered by. And see if we made any mistakes so far. If this even compiles, because I'm not sure I typed everything correctly. Okay, finally. So, since I'll cut out the debugging here, it appears that the leetcode is running either a very old version of Kotlin or does not support a lot of functionality, so I had to rewrite the loops as for loops. And I also fixed a bunch of typos. That's it, that's the only change. Everything else is the same. Oh, and ternaries don't exist in Kotlin, I remembered, and I need to write them as if else, but and trailing commas don't exist, yeah. So anyway, everything else is the same. And we just spammed it out. And what we detected with this input, and this is the initial example they provided. This is the, in the center, this is this example here from the color. And what we see, our output is 2 rectangles starting at 0, 0, going to 3, 3, which is correct. And the second rectangle starts at 1, 1, goes to 2, 2. And rectangle 1 contains rectangle 2. That seems correct. This is where does this work, or do I need to? I want to run a more complex example to convince ourselves that what we're doing is correct. So sorry. Oh, these are multiple inputs. Okay, so this is the first one here. We saw that one already. The next one has a rectangle 3, 3 in the bottom right. On the right side, which is then covered. Let's just pull up GIMP actually. So if that is the second example, these 2 outputs here, please. Then we have 1 rectangle covering the entire area, 1, 1 to 3, 3, that is correct. The color 3 should be covering this corner here, so it's x is 1 and y is 3. 3, and it goes to 3, 4, 2, 3. So we have the rectangle 3 here goes from x1, 2, y1, 1, that is correct, to x2, 3, x2, 3, and y2, 2, which is correct. It's this one. The fourth rectangle should be x1, 3, y1, 2, and 2, 3, 3. That is correct. And 5 should be 0, 3, 2, 1, 3. That is correct. And 5 should not include 1 and 3. we need to investigate this. 1 should include 3, 4, and 5. That is correct. 3 should include 1 and 5, and 4 includes 1. Oh, is this flipped? As in 4 covers 1, but then it should 1, 5. 3 has nothing to do with 5. Okay, so our rectangle detection is correct, but our covered by is not. If the rectangle that is the color we're looking at, and then for every rectangle, if it's a different color and the rectangle includes the row and column, so x, y, y, x. Wait, column is x, yeah. So this is the issue. So if we run this again, then we're looking at the second example here, this one, which makes a lot more sense. 1 contains 3, 4, and 5, and 3 contains 4. 1 contains all of them, and 3 contains 4. Well, is covered by 4. Okay. And the last one should be the negative case. Yep, it is. And it has 2 rectangles, and they cover both the entire area. And we can see that 2 contains 1 and 1 contains 2. So there's a cycle, and that would be our detection. That is what we want to see. Now, how do we do cycle detection? I've talked about graph searching algorithms before. We essentially have a graph here. Our nodes are the rectangles, and the covered by are the edges. Okay. We can solve this part by doing a depth first search. And for that, we probably want to have a recurrent function. Let's declare a function here. DFS cycle, and it returns a Boolean. And as arguments, it takes the graph, of course, which in our case is a map from int to set of int. These are the edges, these are the nodes. It'll take the starting node or current node. It's going to be an int. And it'll contain the path we took to that node, because the way we detect a cycle is we're going to visit the children. So let me do this. So the way we can detect a graph, let's wipe everything. I'm sorry. Let me switch the color. Okay, so now the way we can detect a graph is is if this is our graph, and let's say we indeed have a cycle in here, like so. So we can travel into here. Everything's fine. Then we can travel along the node. Everything's fine. Everything's fine. And now we found our cycle. So if we remember the path we took and we at any point in time find the node as a child that is on the path, we have a problem. So that's what we're going to do. And for that, we need to know the actual path we took there. Right. So for the graph, that is not syntax. So the children are graph of node. The path we want to push the current node onto the path. And then we want to check if the node is on the path first. That's our base case. So if if node in path return true. Otherwise, we're going to return it for any. So if any child, and then we do our recursive statement, the graph stays the same, the node becomes the child, and the path is the new path. And afterwards we need to pop ourselves from the path, so remove last. Then we can return const. Then we can return the result. So if any child is a cycle, then we return true. Otherwise, this defaults to false. The problem is any, when there are no children, also returns true. So we need to do one last check. If children.size 0, return false. We have no cycle if there are no children and we reached the end. This might work. Let's lowercase this because it's a function. And this won't work, but technically now all we need to do is put in our graph. We don't know which node, that's why I'm saying it won't work. And a new deck, an empty one. The problem is we can have multiple routes, like let's say no rectangle intersects, you can still paint multiple rectangles on the canvas. So we'd need to add a pseudo rectangle here. The first one, and that can be color 0. And the rectangle will be from 0, 0 to target grid, it's called. Dot size and target grid size. The outer dimension is the number of rows, so that's the y coordinate, so that should be y2. And the inner dimension are the columns, so that's the x coordinate, so that should be x2. So we have a root. If we look at the problem specification, it says the color is always between 1 and 16. So 0 is a safe value for us to use. And if we run the code, then I used the wrong arrow. And I should use 0 here, because we start with 0. Okay, now that we fixed all our problems, what is nullable? Oh, here it's nullable. In our depth first search, is it? Where is it? Here, it's complaining over this. Because this might be null. And we didn't call it graph, it's called as covered by. I mentioned I'm sick, I'm sorry. I've got a memory of a goldfish right now. Null pointer. Where the hell did we run into null pointer? How did we run into null pointer? What line? Line 34? That's true. We only add them if they have children. If something doesn't have a child, we never add it. So let's just do a new set instead. And supposedly we have the wrong answer. We are outputting false, true, true, and it should be true, true, false, because we need to invert our output here. But that does not explain why this second case fails. True, true, false, true, false, false. Why does the second case fail? The second case is, wherever it marks all of them. This is the second case. What's our graph? It goes 0 goes to 1, 3, 4, 5. 1 goes to 3, 4, 5. 3 goes to 4. There's no cycle here. This should not... This should be fine. Why are we reporting false? because we need to bail before we add ourselves, because we're never removing ourselves otherwise. True. Okay. This should work if we submit it. Success. Probably we could think maybe there's a different heuristic we could detect, use to detect the cycles. Maybe we can use this like bracket words just in the two-dimensional sense and use a spatial tree to detect this, but setting up those data types and using them is going to be a lot more complicated. Yeah, I hope this was insightful, and it's an example of depth-first search and its use. It's not a very complicated algorithm, and if you have any questions, just leave a comment. If you want me to maybe tackle a specific problem, just leave a comment and maybe I'll get to that. Thank you for watching.